What I would like to present today is a piece entitled Archaeo-tectural Translations, an article published in the ACSA's Journal of Technology, Architecture, and Design, Volume 2, Issue 1, and was briefly introduced at the ACSA's 106th Annual Meeting in March 2018. My name is Tim Frank. I'm an assistant professor at KSU in Atlanta and a senior researcher at Gigea Projects. My co-authors, Christina Luke and Christopher Roosevelt, are both archaeologists with affiliations at Boston University and Koch University, and they are also co-directors of Gigea Projects. Gigea Projects is an interdisciplinary research endeavor located in west central Turkey, comprised of archaeologists, architects, landscape architects, anthropologists, and material scientists. Before I begin, though, I would like to acknowledge the many distinguished organizations who have supported the work over the years. The issue we're dealing with in this work is seeing the past through a new lens. What we see here is an archaeological site prior to excavation, in the surveying stage of the investigation. For the archaeologists, the interest in the site is largely focused on improving our understanding of the cultural activities that would have taken place here almost 4,000 years ago. For the architect, on the other hand, the interest is a bit more specific, examining the development patterns of early populations, especially in response to the dictates of both climate and material. However, both disciplines have a shared interest in advancing how one extracts the knowledge embedded within a site like this. So, the main question central to the work is, how can digital technology support the field architect's extrapolation of ingrained knowledge from archaeological datasets? This is probably what we think of when we think of a project of archaeology. In fact, my colleagues in Turkey begrudgingly admit this is something akin to an Indiana Jones film. It is, indeed, an incredibly remote yet beautiful place. What we're looking at here is an active excavation area, and you can see just how incomplete and fragmented the remains are. Yet, this is ultimately how we want to see a site like this, in a much more complete state, where we construe from the cultural fragments a much more holistic understanding of the place. Again, for the archaeologist, it's about understanding how early societies survived, and for the architects, it's about how early builders put resources to task in order to achieve the most basic provisions for dwelling. The more detailed question that we're asking, though, is how does one form an interpretation, especially from such widely incomplete data sets? This is what a hand-drawn reconstruction would look like. Imagine this large fortification wall as a very small mound today. We have to ask, how did the artist come to such a conclusion? And what evidence did they have to make such a large interpretive leap? Fortunately, today's technological advances have ushered new surveying techniques into the field of archaeology, including photogrammetry, remote sensing, and even unmanned surveying, all of which have increased the accuracy and the frequency of the data acquired. What we see here is the process of photogrammetry, which is the science of measurement through photography. And what's produced from the process is a 3D photo composite. It's a mesh that can be imported into an interoperable modeling domain like Rhinoceros, where it is used as the basis for a digital reconstruction model. What can we learn from these shifts, from manual reconstruction to more digitally enhanced methods? One thing we can examine is the process of reconstruction itself, leveraging the vast repository of data digitally acquired today to bolster the strength of interpretations. One of the more common approaches to reconstruction can be seen here in this diagram, where an artifact or sherd is compared to other fragments within the same context group, within the same excavation trench, or even with other objects collected from the same archaeological site. The second layer of comparison would entail identifying articles with similar signatures from neighboring sites, where they were active during similar periods of time in antiquity. Yet, interpretation is incredibly challenging, and with absolute certainty, it's impossible. The incomplete state of remains from thousands of years ago just produce very large gaps in data. On the other hand, modes of prediction used in the architectural design process may be able to help, especially with the use of state-of-the-art modeling and simulation programs. If we use a feedback loop, diagrammed here, common in modes of design prediction, we may be able to increase the level of testing that can be done with digital archaeological data in hopes of strengthening relationships between fragments toward an improved understanding of the site at large. And this is what the hybrid reconstruction workflow would look like. Data from the archaeological record would be input into the interoperable modeling domain, where critical data sets are tested relative to one another to identify key correlations. Two primary data sets are compared. Those are the physical building data and the climate data. The observable output from the testing is evaluated against criteria found in ancient manuscripts and cyclically fed back into the model in the form of geometric reiteration. This gives us the first principles understanding of the structure in its given place. And here's the tool set used in that workflow. Rhinoceros is central, largely due to its interoperability and its ease of geometric modeling. The interoperable functionality is key, especially on an interdisciplinary project, where data from programs like ArcGIS, standard in the field of archaeology, could be seamlessly linked to the base modeling domain. Also, being able to expand the functionality through add-on integration is equally important to systematically test relationships between core data sets. The goal here is to expand the domain to incorporate as many analytical routines as we can. Those in the field who have incorporated state-based simulation tools in the reconstruction workflow thus far have focused largely on specific environmental factors, not taking full advantage of the interoperable programs like Rhinoceros with their wide-ranging functionality. Tools like this allow us to work quickly and productively across the network of most basic relationships that constitute a work of architecture. For us, the holistic behavior of the building is not the sum of its individual parts, so we need a process that gives us the most complete or total picture of the building's behavior. It's the network of relationships that's the most important, and it is why we employ a synergistic approach that's enabled by emerging digital tools. When we zoom into the area here in the middle of the diagram, we get this. The model boundaries are the architectural elements indicated in the archaeological record, such as walls, floors, structure, roofs, etc. While the input states are the regressed climate inputs ranging from pressure to illumination to radiation. It is the observable behavior that highlights the change in state produced by the architectural boundary conditions, and it gives us a better understanding of the boundary state relationships within the domain model. The three main data components within the domain model are physical building data, climate data, and cultural data. Physical data, directly from the archaeological record, is a data set that has expanded significantly with the emergence of digital techniques like remote sensing, which we see here. The process entails inserting a probe at regular intervals where an electrical current is introduced and the resistance to that current is mapped out. Results of which you can see here to the right. It reveals the composition and patterning of buried features such as building foundations, roads, and fortification systems. The second major data set is weather data, which is called from remote monitoring instrumentation installed on many architectural sites today, and it records, transmits, and logs data such as prevailing wind velocities, precipitation rates, and also temperature levels. The science of paleoclimatology aids in the regression of this data, which finds shifts in temperature and precipitation rates in recent millennia, yet presumes the airstream to be relatively stable over a 3,000-year period, while negligible shifts in the orbital tracking of the Earth around the Sun during the same period results in similar sun angles. The third major data set is cultural data, which is obtained through literary sources written in a similar time frame within the same region of development. In the case of late Bronze Era development in west-central Anatolia, this means that we look to ancient Hittite manuscripts that highlight beliefs and recommendations pertaining to the role of buildings and climate in the collective life of early populations. Now let's move to the case study that's presented in the article. Here's the testbed for the methodology. What we're looking at here is called the Siha Riverland, which is in west-central Turkey. And we zoom in to focus on the Hormuz River Valley, today called the Cadiz River Valley. This valley is incredibly fertile, which is one of the main reasons why it has been a magnet for cultural life for so many millennia. Zooming in further, we see the site of Camacha and the primary area of study for Gigea projects. You can see clearly in this aerial photograph the perimeter fortification and the citadel inside. To the north-northeast, you can see the freshwater lake called Marmara today. Here are a few panoramas from the site looking east toward the lake. In fact, it was actually referenced in Homer's Iliad as Lake Giges. There are 6 fortified citadels identified around the lake, exhibiting common signatures of visibility and defensibility, Camacha being the largest of those areas. And here's a panorama looking south from the site, over an area called Bin Tepe, or a land of 1,000 mounds. There are actually 116 mounds that are also called tumulus, which were burial sites for Lydian kings, one of which is almost as large in cubic volume as the Great Pyramid of Giza. Beyond the valley, we can see the Acropolis and the Necropolis of Sardis, the capital city of the Lydian Empire. And this is the trench used in the article. We can see that while the remains are limited, there are distinct foundation and flooring systems still intact, which corroborate the results generated by the geophysical surveys. The architectural features that remain consist largely of local fieldstone, while the mud brick walls and thatch mud composite roofing is no longer present, which substantiates the need for advanced analytics when speculating upon their configuration. So, how is this method used on a site like this, with fairly well-defined wall and floor locations, but nothing over 1 meter above the floor level? Well, we start with the terrain that is surveyed using unmanned equipment, and we find a 6% slope across the area of investigation. These topographic contours are patched to create a similar site surface, to which geophysical traces are projected to outline the foundation walls on the sloping site surface. Together, these data sets begin to identify lines of communication that run along the topographic contours and presumed access points to each structure. The level of each street or alleyway is corroborated against floor levels unearthed during archaeological excavation. The foundation walls are then extruded to approximate the height of walls located in the archaeological record, and the points of communication are explicated. The walls are examined for continuity and spacing to discern whether they could have been load-bearing. Those presumed to be load-bearing are tagged, while the effective span length and direction of the mud thatch support system at that interval is analyzed for feasibility. Once the basic building configuration is modeled from what's present on site, we begin to test the boundaries relative to climate inputs and observe the change in state relative to recommendations found in ancient manuscripts. We start with the solid and continuous overhead plane and use radiation analysis to examine the migration of solar energy into each of the spaces below. We find limited access, which contradicts Hittite manuscripts that indicate the importance of even interior illumination of spaces. So we reiterate the model and begin to introduce roofing offsets with the aim of increasing solar access from above, and we simulate the model once again. The alternative reconstruction shows much higher levels of solar access to the spaces below the roof plane, but the uniformity of illumination is still problematic. So we continue to evaluate alternative building configurations, along with the introduction of new simulation branches, in this case, computational fluid dynamics tools. These reciprocal forms of analysis allow us to understand whether openings overhead served multiple purposes. While terrace development patterns are a common signature in Anatolian development, we can use CFD and ray tracing tools together to see how openings overhead source daylight, while exhausted, hot, or even smoky air from interior spaces below. We can also examine visual communication to ascertain how view sheds out to the hinterland were maintained from more private zones, which was another very important provision indicated in Hittite manuscripts. And the embodied perspective that we see to the right is an essential part of the incremental understanding, to get an understanding of the space and to see how it was perceived as a modulating system of enclosure and protection, Taken together, these initial analytical steps begin to frame important questions about terrace development patterns, the sourcing of resources, and the provisioning for individual and collective action that were latent within this development type. Furthermore, these outcomes can be used to draw correlations to other sites within the region, active during similar periods of time, to continue to identify patterns of development and the possible rationales that underpin them.